everyone. Welcome. Today I want to review for our exam, which will be on Wednesday. So a lot to jam-pack. Make sure you watch this recording when it's done if you miss anything. So I'm going to go a little bit fast. I do have an announcement to make. You hear that noise in the fume hood. I think that's a little bit of a hazard or a risk. So because of that, we will cancel lab Tuesday and Thursday. We'll move it to after spring break. Okay, so if you have me in your class, no lab because of the fume hood. It's not. It's very loud, but I think they're concerned that it could also be a slight risk. Okay, because of all the chemicals, and it's not sucking up the chemicals. All right. So no lab this week. I'll send the announcement out also. Anyone who's not here as absent and you are here, make sure you tell your friends or lab partners, whomever, because of the fume hood, we will not have lab. All right?
Do you know Dr. Howard?
My understanding is no, but you might want to double check. Okay, you may want to double check that. Yeah, I think she's 50-50 because she may move it to a different room. For me, we have a lot of people. I can't put it in a room. This particular lab requires the pH meters as well. Okay. You see that? Hear that? Every 5 minutes. All right, so let's go over this exam. It's Wednesday. I believe that's the 2nd. Make sure you turn in quiz 2 as well. Quiz 2 is also due on that date. So let's talk about the multiple choice a little bit here. Make sure you know what a catalyst does. Okay, what does a catalyst do? Anyone want to mention? Speeds reaction rate. What else?
Lowers
Okay, speeds reaction rate, lowers the reaction time, lowers EA. What is EA? EA stands for activation energy, and what does it do to rate constant K? Well, since Malana said it speeds the reaction rate, makes it go faster, then the rate constant K must go faster as well. Okay, so make sure you know what a catalyst does. How about units of K? Okay, I'm talking about lowercase k. Lowercase k is rate constant, not to be confused with equilibrium constant. That's capital K. This has units that vary. Okay, so let's say we have A plus B goes to C plus D. Okay, and let's say it's first order with A and first order with B. Okay, so rate is equal to K times A times B. Okay, and I tell you it's first order, which means the exponent is 1. And I tell you it's first order with respect to B, so I also tell you that the exponent is 1. Okay? So I tell you it's first order with respect to A and with respect to B. All right, the question I have to ask for you guys is, what's the overall order of this reaction? Not the order with respect to A, not the order with respect to B, but the overall order of the reaction. I hear it? 1 plus 1 is 2, so the overall order of the reaction. The whole thing, yes, is 2. 1 plus 1. Okay, we're doing a test review. Yeah. All right. What are the units of K? Okay, this can be very tricky. What is the units of rate? It's not miles per hour. But what is it? For us as humans driving, or how fast is miles per hour, or whatever units. Here for a reaction, it's going to be molarity over second. Okay, molarity over second is our rate. That's going to equal to K. What is our units of the bracket? What's M? Sophie said M. What's the units of this bracket? M. So what are the final units of K? I'm just talking about units now. Okay, I'm just talking about units. What are the final units of K? Okay, we're going to take M and move it down. M times M is M squared. So this M cancels out with one of those M's, leaving me with 1 over M second, and that will be your unit of rate constant K for this reaction. That's first order with respect to both A and B. So your rate constant is going to vary, okay? Your rate constant is going to vary. What happens if your rate is like this? Rate is equal to K, but I tell you that A decreases with second order kinetics, but B decreases with first order kinetics. What's the overall order of the reaction? 2 plus 1 is 3. Okay, so the overall order of the reaction is 3. Overall order of the reaction, 2 plus 1 is 3. 1 plus 1 is 2, overall order. Units, so this would be m over second equals rate constant K. What is the units of this? It's not m, but m squared. What are the units of the bracket here? I know I'm going fast. M, okay? So one of these m's cancels out with one of these m's. So the units, I'm just talking about strictly units of K for this reaction with this rate law is going to be 1 over m squared second. So you see the units of this lowercase k rate constant are going to vary. Okay, they will vary. Moving ahead here, let's say I give you this reaction, CH4 plus 2H2S is in an equilibrium with CS2 plus 4H2. Okay, so that is your reaction. And these are all gases. Okay. And the whole thing holds 250 ml. And I have 1 mole of CH4. This is called methane. I have 1 mole of CS2. I have 2 moles of H2S. And I have 2 moles of H2. These are all gases. They're occupying this volume, and I have this many moles of that. And here's our balanced chemical equation. These are all gases. Okay. And I tell you the K for this reaction is 0.036 at some temperature, 25 degrees. By the way, K, capital K. Is this quoted at a specific temperature? Yes or no? Okay, true or false? Rate equilibrium constant quoted at a specific temperature? True or false? Everyone say? True. Okay. Change the temperature of this whole reaction, you change the value of the equilibrium constant. All right, under these conditions, are we at equilibrium? All right, here, there's 2 things. Number 1, we need to put the concentrations in K. I'm not going to call it K, I'm going to call it Q. I'm not going to call it K, I'm going to call it Q. And Q is going to equal to H2. What should we do with that H2? Raise it to the 4th. What should I do with that CS2? First power. Products over reactants. What should I do with that H2S? Correct. What should I do with that CH4? To the first power. Okay? Since these are all gases, they go in. Do you see a solid here? No solid. Will you put a solid in here? No. Will you put a liquid in here? No. What do I put here as my concentration? Do I put 1 mole? What's my concentration of CH4? Is it 1 mole? The concentration is what units? We're in Chem 2 now. So concentration is in what units? Moles over liter. Okay, moles over liter. So what is the concentration of CH4? It's not 1 mole. It's 1 mole over 0.250 liters. Okay, 1 mole over 2.250 liters, which is, I believe, 4m. What is my concentration of CS2? It's not 1 mole. We're in Chem 2 now. Concentration is moles over liter. It's 1 mole divided by 0.250 liters, which is also 4 molar. What's my concentration of H2S? It's 2 moles divided by 0.250 liter, which is 8 molar. And what's my concentration of finally H2? It's 2 moles divided by 2.250 liters, which should be 8 big M. Now I put into my equilibrium expression Q. H2 is this, that's 8 to the power 4. CS2 is 4. H2S squared is 8 to the power squared. And then CH4 is 4. Okay, so the 4's cancel. The 8 squares cancels, leaving this with 8 square. So Q is 64. Are we at equilibrium? If equilibrium is 0.036 and we're getting 64 under these conditions, under these concentrations, are we at equilibrium? Okay. Heck no, we're not. Okay. Which way will it go to get to equilibrium? Okay. Here you're going to use what's called the Gator rule. Okay. So what will we put first in the Gator rule? Q or K? Q or K goes first in the Gator rule? Q is right. And then what comes? K. So what is our Q? 64. What is our K? 0.036. Okay, which is bigger? Okay, which way will the reaction shift to get to equilibrium? Where do the alligator jaws point? Towards the reactant side. So this will be on your exam. Okay? Something like this. So it's very key on this type of problem that you will encounter that what you put into your equilibrium is moles over liter. So you're going to take this moles over liter, this moles over liter, this moles over liter, this moles over liter. Okay. Once you get that, you're going to compare it to K and then use the Gator rule to determine which way it will go to be in equilibrium. All right. So definitely look this over on your quiz and also your homeworks. So that will be on the exam. And don't forget K is quoted at a specific temperature. Okay, don't forget that. All right. Gonna move on here. Okay, I'm going a little bit fast, trying to hit as much as I can. Okay, definitely watch the recording if I'm going too fast. All right, how about Le Chatelier's principle? We had a lab on this just last week. Okay, so here we have 2H2S plus O2 is in an equilibrium with 2S plus 2H2O. Okay, so there's several things I can do with this problem here. Let's call this a gas. Let's call this a gas. Let's call this a solid. 2S is sulfur. And let's call this a liquid, okay? For whatever. So there's several things we can do. Okay, let's say we remove S, solid. Okay, where will the reaction go? We take this away. So where will the reaction shift? To the right or to the left? If we remove sulfur, where will the reaction shift? Okay, we take some of this away, so what will the reaction do? It offsets what you do, so offsetting what I will do, or what is done, will make this shift to the right, to the product side. What happens if I remove oxygen gas? Okay, if you remove it, the reaction will offset it and shift to the side to replenish the O2 removal, so it's going to shift to the left. Okay. Like that, we have many different combinations that we can do. How about we add water? Shift left to the reactants.
Wait, if we add it to which side?
You add H2O. You're adding product.
From the products to the reactants? Is that what you're saying?
If we add H2O liquid to this equilibrium, where will the reaction shift? It'll shift that way. It'll shift that way, right? If you add some of this, the reaction will shift that way to remove the H2O that you added. If you remove O2, the reaction will shift this way to add the O2 that was removed. If you remove sulfur, the reaction will shift this way to add the S that you removed. So it does the opposite, okay, offset. Okay, so that is Le Chatelier's principle. It's an offset. What happens if I remove H2S gas? Where will this reaction shift, Milana? I'll ask you. It's going to shift. You remove this, so the reaction is going to go opposite, which would be to the reactant side. Okay, shift left. So, question on like this on the exam. Also, I believe it's on your quiz as well. So, what if we have a reaction like this? We take some calcium oxide, we add some water to it, and we make calcium hydroxide. Okay, this solid. The delta H for this reaction, remember delta H? The delta H for this reaction is minus 82 kilojoules. So is this an exothermic reaction or an endothermic reaction? This is an exothermic reaction. So there's only two things you can do to an exothermic reaction. Okay, you can add heat, which is raise the temperature, or you could lower the temperature. What happens if you raise the temperature in an exothermic reaction? Okay, don't forget, in an exothermic reaction, you release heat. Exo means outside. Exo means outside, which means heat gets released. So what happens if you raise the temperature? You're adding heat. Which way will the reaction go? it will react. It will go to remove that heat, so it's going to shift to the left. Okay, reactant side. What if you lower the temperature? Lowering the temperature means you're removing that heat in an exothermic reaction. If you remove that heat, where will the reaction go? It will go to the side to give back that heat, and that is to the right. So that is what will be the situation for an exothermic reaction. How do I know it's exothermic? Right, the negative. Okay, the negative sign. What happens if this was positive? It's not exothermic, but endothermic. All right. Right, so question like that on your exam Wednesday. Okay, I think I mentioned this before, but want to reiterate it again. No solids or liquids in the K, big K, equilibrium constant. Okay, which is products over reactants, but no solids, no liquids. Okay, so that is a multiple choice question. If you're asked to write the equilibrium constant, okay, and if you see a solid in there or if you see a liquid in there, you're not going to put it, okay? No solids, no liquids in the equilibrium. The only thing that goes into the equilibrium are aqueous and gases, okay? If it's an aqueous, meaning dissolved in water, then it goes in. If it's a gas, then it goes in, okay? All right, some questions here on rate laws. Okay, there's a first order rate equation. Okay, so make sure you bring that rate law sheet to the exam. Bring that rate law sheet. Law. Okay, so there could either be a zero order, first order, or second order. Okay, you know what I mean by rate law sheet, right? Have that? So this is what you can have for the exam, so make sure you have it by your side. This one. So have this by your side during the exam, okay? So you can utilize some of these equations for some of these problems. As an example, let me give you one example problem here. First order, it's a decay. All of these are decays. Okay, when I say decay, okay, how are you going to decay? Are you going to decay with zero order kinetics? Are you going to decay with first order kinetics? Are you going to decay with second order kinetics? If you're going to decay with first order kinetics, okay, here's the equation that you will use. Again, I just copied it from our sheet. Natural log of the concentration of A at some time t equals natural log initial minus kt. Also, this is for first order decay. Okay, there's also a half-life for a first order decay. What is half-life? The definition of half-life is the time in which 50% of it is gone. Okay, for first order, it's this equation, natural log of 2 over k. So as an example on the exam, let's say you have the half-life of something is 12 years. And you know it's first order decay. That means after 12 years, 50% of it has gone. Okay, you know radioactivity and stuff like that. Okay, it just decays. After 12 years, this substance, 50% of it is gone or decayed after 12 years. So how long will it take to go from 10 parts per billion? How long will it take to go from 10 parts per billion how long will it take to go from 275 parts per billion to 10 parts per billion? The PPB stands for parts per billion. We don't really need to concern ourselves with that in terms of the answering this question. We start out with 275, we go to 10. How long will that take? If it's first order decay, and this is the half-life. Okay, so do we know how to solve this problem? Okay, so we're asked for a time, so we have to solve for time t. So k is going to equal to the natural log of 2 over the half-life. Okay, they tell us the half-life in this problem is 12 years. So natural log of 2 is 0.693. Okay, you can look that up in your calculator. Divided by 12 years. And this is about 0.05775 on your calculator. Okay. Inverse years, because the units are years to the -1. So we got our half-life. We solve for k. And then we can put k in here and then put it into our equation. So it's a decay. It's a decay from 225 to 10 parts per billion. And it's first order. So this equation is what we'll use. Okay, use that on your exam. Natural log of, we want it at 10 parts per billion. Natural log of 10 is final. Initial, this is initial, equals 225 minus k, which is 0.05775. Divided by years times t. So, first order decay problem, the half-life is 12 years. How long will it go from 225 ppb parts per million to 10 parts per billion? Okay, that's a decay. We figured out the rate constant, lowercase k. We plugged it in. Initially, we're at 225. Finally, we want to figure out the time it gets to 10. And we just solve for this. Okay, do we know how to solve for this? Okay, putting that years in the denominator within a denominator flips it back up to the numerator. And whatever this answer is on our calculator will be the answer. All right, so this is the flow through that you'll have to use on your exam for that particular problem.
Is that a negative in the front? Is that a negative in the front?
Yes, because I'm dividing it by a negative 0.05775. Right, so natural log of 225 goes here. Natural log of 10 minus natural log of 225 divided by minus 0.05775. So whatever that is will be your answer. So a problem like this on your exam, maybe the numbers are a little bit different. about 54 years. It should be positive because the minuses cancel out. Natural log of 10 minus natural log of 225, negative, divided by a negative 0.05775. Yeah, 54 years. So it'll take 54 years for this substance, whatever that substance is. Because it's first order, it used this specific equation. It will take 54 years to go from 225 parts per billion to 10 parts per billion. Okay. So, question like that on the exam. All right, this Gator rule, I should also mention, will be on your written portion of the exam. Okay, so the Q rule, okay, so let's say you have this reaction. Then I tell you the Kc is 4.19 times 10 to the minus 9. Okay? And the concentrations that you set up to do this reactions are this. Are we in equilibrium? Yes or no? We don't know. Okay? We don't know. What you have to do is plug this into the equilibrium constant, which is H2 cubed times N2 divided by NH3 squared. Okay? Now, if you plug in these concentrations in here and it equals to this, are we in equilibrium? The answer is yes. Okay, what happens if it does not equal to it? Okay, just like in our previous problem before, one of these problems here, okay, we have to compare it to K. Okay, we have to compare it to K. So when we compare it to K, if it's greater than K, reaction will shift this way to get to equilibrium. If you plug in these numbers here and it equals to K, you're already at equilibrium, right? And finally, if Q is less than K, which way will the reaction shift to get to equilibrium? Where do the alligator jaws point? Okay, they point to the product side. Okay, so this will be on your written portion of the exam. Right, I must ask you this. A lot of students seem to not get this here, but so let's say you have this reaction here. 2NO plus H2 is in an equilibrium with N2 plus 2H2O. And then the K for this reaction, Kc, I'll just put it, is 650. Okay. 650, which way will the equilibrium favor, product side or reactant side? 650, is it greater than 1? If it's greater than 1, it will favor the product side. Okay. All right, so there's a couple of things I can do to this reaction. Okay. Here it is. Here's the equilibrium constant at some specific temperature. We can call that 25 degrees. Okay, that's not the point. Okay, the point is, what happens if I flip this reaction? if I flip this reaction, what will be my new equilibrium constant?
Is it
Will it be negative 650? Okay, what do you do with the equilibrium constants if you flip it? If you flip the reaction, what happens to the K? Okay. You take the reciprocal of it. You take the reciprocal of it. What happens if I want to take this reaction and multiply it by 2? Okay, so it'll be, multiply 2 throughout this equation. 2N2 plus 4H2O goes to 4NO plus 2H2. What is my new equilibrium constant? Okay, I multiplied everything out by 2. So what will be my new Kc? My new Kc for this reaction will be squared. Okay. So flip a reaction, you take the reciprocal. And that's your new equilibrium constant. You multiply by 2. Like I did here, 2, 4, 4, 2. I just multiplied this out by 2. My new equilibrium constant becomes squared. Okay, products over reactants. No solids, no liquids. If I multiply this by 3, I cube it. Okay? So those are the rules governing equilibrium constants and the reaction. Okay, so make sure you know that for the exam. Okay, what happens when we play with the equilibrium constants in such a way the new equilibrium constant will be take the reciprocal if you flip the reaction. If you multiply a reaction by a number, you take that number and it becomes the power. The new equilibrium constant is the power. Okay, I think a couple of more things here. We've got maybe about 10 more minutes or so. So look over these. Question about activation energy for you guys. Okay, what is the activation energy? Activation energy is the energy that you must be overcome. Okay, it's like a hump. Okay. Activation energy is a hump, an energy that you must overcome. Okay, what does it depend upon? Okay. So remember, if two reactants are going to react, they can't just react any random way. Okay, they have to react in a very specific way. So we call that collision frequency and orientation. It's not like, oh, they react, A plus B will react to give you C plus D. It's not like that. Okay, they have to be a specific orientation, and they must hit each other with enough velocity or enough frequency. It cannot be a wimpy collision, and it cannot be any old collision. Okay, so it has to be the right frequency, and it has to be the right orientation. This will not do it. This will not give you the reaction. This will give you the reaction. Okay, so for an activation energy, we need the right collision frequency, and we need the right orientation of A to B. Okay, and that is why it is sort of a hump here. Okay, that must be overcome. To get A to be in the right orientation, to get B to be in the right orientation, for them to hit with enough force to give you C and D. Okay, all of that factors in to your activation energy. Okay, it's that energy that must be overcome. In order for that energy for it to be overcome, you need the right orientation and you need the right frequency. All right, there's a question here on your exam. If you have AB is going to A plus B, okay, and the rate is equal to KAB squared. This decays to second order kinetics. Okay, second order kinetics. Okay, so make sure you know how to use the equation for this decay. The equation for this decay is 1 over AT equals 1 over AO plus KT. Okay, so that will, application will be on your exam. Okay, what is AO? Is that initial or final concentration? Okay, this is also known as A naught. That's the initial concentration. What is T? Some concentration of A at time B. Okay, actually it's going to be AB because AB is the reactant. Right, so that's on the exam. How about I ask you this? What happens if I give you this and say it is zero order kinetics? Okay, zero order kinetics. Or zero order decay. What does that mean? What is any? Okay, so here's second order kinetics for this reaction. Here's zero order kinetics. What does this mean? Okay, what is anything to the power of 0? So if this decays, AB decays with zero order kinetics, your rate is equal to K. So what are your units of K then? What will be your units? Okay. Molarity over seconds. So you have to recognize, and I believe it's on your quiz, okay, zero order the units of K, first order the units of K, second order units of K. But if it's zero order and it's like this, then yeah. Okay. Your rate is equal to K to the power of AB. Your rate is equal to K times AB to the power of 0. Anything to the power of 0 is 1. So rate is equal to K. The units of rate are molarity over seconds, which is the units of K. Okay. Right, so just check your units of K before the exam, okay? For zero order, first order, and second order. Okay, before you take your exam, make sure you review that. All right, I won't do this, but there is a rate law problem. Okay, are you guys comfortable in doing this the last 5 minutes of class or so? Okay, a rate law problem. Okay, this is called a rate law. So in a rate law like you did in your lab, okay, you'll have to find K. You'll have to find the order in which NO2 decays. It could be 0, first or second order. You'll have to find the order in which CO decays. It can be 0, first or second order.
Is this not in equilibrium?
It can be in equilibrium, but we're just interested in the rate law. Okay, so we're interested in this law. It can be in equilibrium or not. Okay. Yeah. Okay. Don't confuse rate with equilibrium. They're two different things. Okay. So this is how fast, and this is where the reaction settles. Okay, more reactants or more products. Okay, this is lowercase k. This is capital K. To figure out the rate law, you're going to need a table. Rate. And usually they do this, people who do this, they actually do this 3 or 4 times. Okay. This is what you guys did in the iodine reaction. So at an NO2 concentration of 0.1 and 0.1, we have 0.0050 as how fast the reaction goes. Molarity over second, some concentration over time. Okay, we increase this reactant by 4 times. Keep CO the same, and that's going to be, this is 0.080 molarity over second. Here we double CO, we double carbon monoxide CO, and we keep this the same. We get 0.0050. And so this is given to us. Do you know how to calculate the rate law for this? Right, how will you do that? Okay, so you're going to compare reactions, right? Compare experiments. So you can compare experiment 1 and 2, let's say. So rate 1 over rate 2 equals K times NO2 to the power of A times CO to the power of B divided by K times NO2 to the power of A times CO to the power of B. So this is rate 2, experiment 2, rate 1, experiment 1. Now you just plug everything in. You remember how to do this? We did a couple in class. Rate 1 for experiment 1 is 0.0050, big M over seconds. Rate 2, experiment 2 is 0.080, big M over seconds. Okay, what's the concentration of NO2 for experiment 1, rate 1? Okay, it's going to be 0.10 to the power of A. What's the concentration of CO, rate 1, experiment 1? It'll be 0.10 to the power of B. Okay, we plug in the same thing, comparing experiment 1 to experiment 2, putting in experiment 2 values. And like that, we can go ahead and find the order A. Okay. How will we find the order B? Maybe we can compare experiment 1 with experiment 3. Rate 1, rate 3, and it's the same thing, okay? Plug in the numbers. Okay, so rate 1 for experiment 1 is 0.0050 molarity over second. Rate 3, experiment 3 is 0.0050 molarity over second equals K NO2. NO2 for rate 1, experiment 1, 0.10 to the power of A, CO, 0.10 to the power of B. Okay. And like that, we're going to plug in everything. Experiment 3, rate 3. Plugging everything in, we should be able to get our exponents A and exponents B. Okay, do we know how to do that? Okay, watch some videos on Canvas that I have recorded to get the complete details of this problem. And then once you do that, once you find exponent A and exponent B, you're going to have to figure out K, okay, with the right units. So before you take your exam, make sure that you're comfortable doing a problem of this sort, because there'll be a rate law problem like this on the exam.